Welcome back, geologists. We left off talking about city water systems and how they are like a flowing artesian system. I want to talk about springs today. So this is video 3 for chapter 17, groundwater. A spring is simply a natural outflow of water when the water table intersects the ground surface. Many situations can cause springs. This is Thunder Spring, and it emerges from a limestone in the north rim of the Grand Canyon. And it emerges along a joint system that is located very deep and a cave system as well. Hot springs, by definition, is water that is 6 to 9 degrees Celsius warmer than your average annual air temperature of the location. And there's a lot of hot springs in the United States. Most of the time, this water is being heated by igneous rocks. Some hot springs are warmed by the geothermal gradient. An example of that would be in Georgia, Warm Springs, Georgia, where this geothermal gradient is steeper than normal. This shows a map of the United States where clearly most of our hot springs are located west of the Rockies. That's where our rock is younger and warmer. There are still some locations on the East Coast from the Appalachians, and here is the Warm Springs, Georgia, and Hot Springs, Arkansas as well. A geyser is a hot spring, but it erupts at various times. How this occurs is there needs to be underground chambers near hot igneous rock. So the groundwater is getting heated by that hot igneous rock, and it's also under a lot of pressure. So because of the high pressure, the water is not allowed to boil. However, when the water starts to expand and some of the water is forced out of the geyser, then the pressure is reduced below that point, allowing for the geyser to erupt. Here is the very famous Old Faithful at Yellowstone. A visual is probably better to show you how a geyser works. First figure here, the water near the bottom is heated to close to its boiling point. It's not going to boil because of the pressure that is being exerted on it from the overlying water. Now, higher up in the geyser, the water is also being heated, and it expands, causing some of it to outflow at the surface. That allows the pressure to decrease in the lower part of the chamber. And with that, the boiling occurs, and the bottom of the water flashes into steam and expands, allowing the whole eruption to occur. There are a couple different sedimentary rocks that form as a result of geyser deposits. This deposit is travertine, and that is a form of limestone. Another example of a geyser deposit is geyserite, and that's made out of silica rather than calcium carbonate that travertine consists of. Groundwater should be treated as a non-renewable resource. In many areas, it is being extracted at a faster rate than it is being recharged. A good example is the High Plains Aquifer, also known as the Ogallala Aquifer. It is one of the largest and most agriculturally significant aquifer, accounting for 30% of all the groundwater used for irrigation in the U.S. The High Plains Aquifer shown here, in the red areas, we have water level declines in more than 150 feet, and then 100 to 150 feet in the slightly lighter red color, and so forth. So you can see that in parts of Kansas, the Panhandle of Oklahoma and Texas, water is being extracted at an extremely high rate, and eventually they are not going to be able to use this aquifer anymore for irrigation purposes. One other note about this slide, this is a decline in water level over the past 60 years. Subsidence is another environmental problem with overpumping of aquifers. A good example of this is in the San Joaquin Valley of California, where the subsidence has approached 9 meters. Subsidence generally occurs in areas where the water has been extracted from unconsolidated sediments. There is no water to hold those pore spaces open anymore, and the overlying weight of the material on top simply closes the pore spaces up. There is no way to reopen those pore spaces. Here's the San Joaquin Valley in California, and this is a telephone pole showing that the land height before groundwater pumping in 1925, and a decrease by 9 meters, which is 30 feet, by 1977. Another evidence of subsidence is this crack here in the earth. The location of this subsidence example is in Arizona, where there has been more than a decline of 600 feet in the water table. Saltwater intrusion is another environmental problem with extracting groundwater at high rates. We generally don't have to deal with that since we are landlocked here in Missouri, but let's take a look at it. Here we have the ocean, a well that is put into an aquifer of fresh groundwater, and because of over pumping or excessive pumping, the water table is lowered and the base of the freshwater zone rises, causing the salt water to be allowed to intrude into the well, rendering it useless. In Long Island, New York, there are over 2,000 recharge basins that have been built in order to allow water to slowly infiltrate back down into the aquifer, recharging it. Without this, they would not have enough water because Long Island relies on almost all groundwater. By recharging in these basins, you also prevent saltwater intrusion into your fresh water. Raw sewage is a common groundwater contaminator, and sometimes this is coming from people who have septic systems. Let's compare two aquifers. Start with the top picture here. We have well 1, and the neighbor has a septic system here. It is leaking, it's contaminated. But the main issue with this contamination is that it's traveling through cavernous limestone. That is limestone with great big openings in it. So the water travels quite quickly and gets into well 1, delivering contaminated water to that house. And we're talking days or weeks as far as a time frame. Now, if we look at this bottom picture, what we have is not a cavernous limestone underlying the homes, but a nice sandstone. When the septic tank is leaking and hits the aquifer, the water travels, the contaminant travels much more slowly, and it cleans itself by the time it gets over to this well. Many contaminants will naturally clean themselves with time, and sometimes that's our only options in cleaning up contaminant waste, because it is simply too expensive to do anything else but just sit back and wait for time to clean it up. Other sources of contamination in groundwater includes the salt that we de-ice our roads with, fertilizers that run off of yards in suburbia, as well as farmland, pesticides, chemicals, and industrial materials. In this picture, the outflow from the septic tank originally is going away from the well. In the second picture, because a new well has been installed and pumped heavily, it has actually reversed the flow of the septic tank effluent, and now it is coming up through the well into these people's house. Other sources of groundwater contamination include leaking landfills, as well as leaking underground storage tanks that contained gasoline. Most groundwater is mildly acidic and will dissolve carbonate rocks such as limestone. As a result, caverns and caves form. This is a very famous Mammoth Cave in Kentucky, a big tourist attraction. As groundwater travels through carbonate rocks such as limestone, it dissolves the rock away, forming caverns and caves. The continued dripping of water within these caves forms speleothems. That is a general name for all dripstone features. And stalactites hang from the ceiling, and stalagmites form on the floor of the cavern. And if they happen to grow together, they form what we call a column. Here's an example of a column. This is stalagmite and stalactites hanging from the ceiling, and this is a soda straw that is dripping water and precipitating out calcium carbonate. In areas that have been extensively affected by dissolution of limestone, a certain topography called karst topography develops. Common features that we see in karst include irregular land or terrain, sinkholes, a lack of surface drainage, and even tower karst. I'll show you a picture of that. This is the development of karst landscape with time. So this is an early stage, and you can see that with progression of time, eventually the water table drops down very low, big caverns are forming, you get sinkholes and sinking streams, or what I call disappearing streams, solution valleys. So if you see this distinct pattern in an area, it's indicating karst topography, and you should be careful if you plan on building in an area like that. A couple other incidents of sinkholes in New Zealand, and this is in Lake City, Florida. Looks like their house is partially fallen into this sinkhole. This is the most distinctive tower karst in the world, and this is in China, and you can see these beautiful features that have been formed due to dissolution of the limestone. So this is an extreme case of karst. That ends our discussion on groundwater, and it's been a great semester. So I hope that you, when you are out driving around and looking at the landscape, that you will notice all of these geologic topics that we have covered throughout the semester. It's been nice having you as students.